Let's go fairly fast because some of this should be reused, like what a sugar or what carbohydrates are and what, in general what that means. And so I kind of already give it away, but what are examples of carbohydrates? Like in your diet, what's an example of a carbohydrate? Bread. Okay, rice. But what are those made up of? If we break that down, what makes it a carbohydrate? Sugar. There are sugars, starches, things like that. Okay? All right. Most of these that we're talking about are called polysaccharides, where the basic building block is a monosaccharide. They have lots of functions inside your body. Lots. Of course, some of the simplest ones are just for energy. We talk about blood glucose levels. Sucrose. What is sucrose? What is sucrose? Sucrose is just table sugar. I'm saying the simplest thing. This is your table sugar, like the kind that you would get. That's sucrose. Glucose is, what is glucose? What kind of sugar is it? I mean, it's got 6 carbons in it, but what kind of, biologically speaking, what kind of sugar is glucose in your body? That's your blood sugar. Whenever you take blood sugar is taken, that's your glucose level. And we'll talk a lot about that kind of stuff. And what I find much more interesting than just learning about tetrose versus pentose and all that kind of stuff next semester in greater detail. All right, the ones that are most common that are found in nature of the monosaccharides range in the size of carbons, either those that are called triose, if they have 3, all the way up to 8. Okay, and they were called carbohydrates because the vast majority of them had this general formula of 1 water molecule for every carbon in the actual chemical formula. But we're going to find out that's a big oversimplification, major oversimplification. So, but the name carbohydrate stuck around. Okay. And then we had the 2 broad class. Oh, and one thing I wanted to point out is about there's the ending. Ose is the ending for these sugars. Whereas, what's the generic ending for enzymes? ACE. So make sure that, and I try to do it myself too, that whenever I draw things out, that it's obvious an ose versus an ACE. Okay? But ose means it's a sugar. So what do you suppose, if you think back to organic chemistry, a ketose is going to have in it? A ketone, and an aldose would have an aldehyde. Okay? So those are the 2 broad categories. As I mentioned before, in fact, I'm just going to give it away just to save time, is the fact that usually the monosaccharides are classified by the number of carbons that they have. So 3 would be triose, tetrose is 4, pent would be 5, hex, hept, and oct. Those are the most common. Now, to make things more interesting, is then you could, in theory, have something that would be, for example, a keto tetrose, or it's much more specific. That specifically lets you know there's 4, it's a sugar, it's got 4 carbons, and it has a ketone in it, versus an aldotetrose, or a tetroaldose, or tetraketose, depending upon the way that they word it. But I would expect that you'd be able to take those 3 parts of the word. I've been teaching medical terminology too much, so I don't think about it too much. But if you break the word down, then you can follow along. The aldo or ketone means it's either an aldehyde or ketone. Tetra would be 4, and the ose would be the sugar. Glyceraldehyde is one that technically I have told you that you haven't had to memorize the names yet, but you probably should by now start picking up. Next semester you're going to have to know all the glycerol-based ones. And so it's really simple. How many carbons are in glycerol? 3. And what makes glycerol glycerol? What's the functional groups on glycerol? There are all 3 alcohols. And so this is why glycerol, if we were in organic chemistry, of course there'd be 2 hydrogens here, 1 hydrogen, and 2 hydrogens. In organic chemistry, we would call it 1, 2, 3 propane triol. or propane 1, 2, 3 triol, but in biochemistry and biology, it's just easier. It's glycerol. Well, let's want to say I would say, well, next semester you have to memorize it, but if you know glycerol, then you know glyceraldehyde. All you do is you literally take one, it doesn't matter which of the terminal oxygens, but you turn it into an aldehyde. And so that's why it literally means a glycerol backbone, but there's an aldehyde on it. But that's the simplest of the monosaccharides, is glyceraldehyde. And by the way, it is an aldotetrose. The keto tetrose is called dihydroxyacetone because it looks just like acetone, but it has two extra, two alcohols on the end. That's why dihydroxyacetone. Okay, but they do have enantiomers, and so the enantiomers are based off of, the sugars are based off of using the terminology off of glyceraldehyde, which is different than it is for organic chemistry in the sense, and the reason why is once you see with these more complicated sugars, is you can have a lot more chiral carbons in it than just one. Okay, so we have to have a way to differentiate rather than, one thing I would not have you do, maybe this is one of the reasons why I have an aversion to this chapter. Whenever I took Biochemistry 1, we had to memorize all of the simple sugars, all the way from 3, glyceraldehyde, which was the simplest, and dihydroxyacetone, all the way through the 8. And so we came up with ways to do the memorizations, and it's completely worthless. And so I don't make you do that, but that's why I spent like the entire chapter just trying to do that. But they have to have the ones that are more complicated. So for example, this one, this is the Fischer projection, if you think back to that's supposed to be a double bond right here, by the way. I just can't draw it very well because I wanted to draw an example of a ketose. Whoops, there is no. Whoa. Oh! Well, let me try this again. I put in one too many bonds. It doesn't really matter so much. Oh, this one's much better. How many? So whatever one that you drew before is fine. Okay, but this is just an example. And I wanted to show you that the fact that there is more than one chiral carbon, so we have, this is a chiral carbon, this one's a chiral carbon, and this one. And so we have to have a way to differentiate between the two possible enantiomers of this specific sugar, given their names. And so what they do is they look at what's called the penultimate, which is just a fancy word for next to last carbon. And so this is the last, so this is the penultimate one. And you look to see if the alcohol is on the left or the right, and you just base it off of glyceraldehyde. And so that's why this would be the L sugar, and the D sugar would look just like it, except this alcohol would be on the right-hand side. Okay, so once again, it's just based off of, the enantiomers are based off of the backbone using glyceraldehyde since it's the simplest, and not based off of any of the other ones. And then once again, this will make more sense once we start looking at some of these.
So alcohol on the left is L.
And so, once again, this is just an example. This was the simplest two, which this one, based off of organic chemistry, I would expect you to know. If I told you dihydroxyacetone, you had to know acetone from organic chemistry, and you literally just put an alcohol on the two terminal carbons, that's dihydroxyacetone. But it's the simple of the keto trioses, because it's a ketone with 1, 2, 3 carbons in it. This glyceraldehyde is the simplest of the aldotrioses. In fact, these are the only 2 trioses they're possible, because we have an aldehyde in 1, 2, 3. Then we can get to glucose. Glucose has 6, 1, 2, 3, 4, 5, 6. It's an aldose. So So technically it's an aldohexose. And this one's D because the penultimate carbon has the alcohol on the right-hand side. Whereas they don't show you the L, but the L would have it over on this end. And so, okay, and then I wanted to point out the fact, and you should already have a feeling for this from biology in general. Of course, this is ribose, okay? And this one's deoxyribose, where you can literally just remove or modify. Some of them, you can make even amino sugars, where you replace one of the alcohols with an amino group, but they can be modified. Of course, riboses, it's an aldopentose, but what does it use to make in your body? What's one example of a ribose? RNA, so right, ribonucleoproteins, or that's an RNP complex, but RNA, ribonucleic acids versus deoxyribose, of course, would be for DNA. Of course, this is not the way that you're used to seeing it from biology. This is its non-cyclical, its linear form. And I actually have already, this is just a quick review. Fischer projections, remember, if it's on the horizontal, it's coming out towards you. If it's on the vertical, it's going away from you. And once again, it's all based off of glyceraldehyde. If the alcohol is on the right-hand side for the penultimate, then it's going to be a D. If it's on the left-hand side, then it's an L. And so that's why I'm going to actually just skip ahead to where we can look at some examples. Here we go. So if we look here at this top one, the top left, all of these are hexoses, because see, they've already numbered the carbons for you. So all of them are hexoses, but is this one right here, is this an aldohexose or a ketohexose? It's an aldohexose because it's got the aldehyde. And then finally, is it a D or is it an L? D, because once again we look at that penultimate, the next to last one, and it's still on the right-hand side. Okay, whereas the only difference between these two is the fact that this is the keto version of it, but once again it's D. Of course, this is L. Okay, and this one would be D. Okay. Whoops, I went too far. All right, so then we have 4 possible aldotetroses. You have D and L erythrose and D and L threose. And one thing that I want to point out, which is different, and you may have forgotten this, but in organic chemistry, we would many times give these completely different names because, let's see, that's not the right way of saying it, but that's not why I'm not going to say it that way. But what I wanted to point out is the D-erythrose. To make L-erythrose, you have to do the full enantiomer. It's not just switching the one, because if you just switch one of them, you're going to ultimately turn it into threose. So it's literally, they name the sugar, so this one's erythrose, and then to do the enantiomer of it, you have to completely do the mirror image of it in order to get it to become L-erythrose. Okay. Then just to use some other, I've already been using these terms, but enantiomers literally are just stereoisomers that they're mirror images that are non-superimposable upon each other. So like your hands, they're mirror images, your right and your left hand, but if you line up your middle finger, your thumbs and your pinkies don't line up. Okay, so they would be enantiomers. A diastereomer are stereoisomers that are not mirror images, and that happens when you have at least 2 chiral carbons. So that's why, if we look at this, erythrose, D and L erythrose would be enantiomers, but erythrose compared to threose are called diastereomers. That's just a little terminology there. This is just a little cartoon showing the exact same thing that what what I've been saying. This is the kind of thing that we saw in organic chemistry with a little mirror, and you could do R versus S. It's just that in biochemistry they like to use the terms D and L for dextrorotary and levorotary. Dextro is the prefix for right, because it would rotate light to the right, and levo means it would rotate it to the left, because levo is a prefix for left. Okay. Moving on along. This is what you're more used to seeing the sugars with respect to, like when we talk about DNA and RNA and looking at the sugar backbone. This is what you're used to seeing them look like, are called Haworth projections. Okay, that's because you can imagine, and this is especially true for anything that has at least 5 or 6 carbons. But we have nucleophiles. So here, let me just draw a little example here. That way. That's supposed to be an aldehyde at the top. I just want to use that as an example. And the same thing can happen with the ketone. I just did the aldehyde version. But we have multiple nucleophiles in here. Because remember, what does a nucleophile, what must a nucleophile have in order to work? Lone pair electrons. So we have lone pair electrons in this alcohol, this one, and this one. These are the two that would be the most reactive, or have the highest ability to react, because we have all these nucleophiles, but we also have an electrophile. That carbon right there is electron deficient. That's what they're showing right down here. So it's easy to be attacked. And so it literally can attack itself. Okay, and if you think back to organic chemistry, we have the acetal versus hemiacetal, and that's just a fancy word for this, the ability for the aldehyde in this instance to have the alcohol come and attack itself to form a new alcohol on the other end, to break that double bond. And whenever this happens in vivo, or even in vitro, but it's going to make a cyclical, it's going to make a cyclic molecule. And so that's why you're more used to seeing, that's how you're more used to seeing the sugars drawn. And what I mean by that is RNA, you know, the sugar behind it, you're used to seeing it look like this. Okay, and then we'd have something right there. Of course, if this was for the actual nucleotide, that would be like, you know, A, U, or G. Why am I not seeing? Or C. Whoops. I'm like, no, there's a fourth one. That's supposed to be a C. That's not that important part. But what I'm saying is this is the Haworth projection to show you that it's cyclical of ribose. That's really, really sad. That was my grandmother, and she passed away. And so, but yeah, today would have been her birthday, and her Facebook page is still up. And so, you know, but now she's spending, you know, her birthday up in heaven with my grandpa and with, you know, Christ and God and everything, which is, it's sad for us, but it's good and glorious for her. Which, by the way, she passed away on my birthday. Yeah, that was a rough birthday. Not this year, it was last year's birthday, but okay. Okay. So this is just to show you where you could do, it's called the hemiacetal if it was an aldehyde, which I wouldn't ask this on a quiz or an exam. It's called the hemiketal if it was on the ketone, and of course you can go ahead and react it a second time to make ketal or acetal version forms. Alrighty. So this is the important part, and the way to do this, okay? There are two possible ways that this could happen. Come on now. So they're showing already, this is the nucleophile. This is going to be the carbon that gets attacked. And to draw this, the way that they draw this is they literally take it and they rotate it 90 degrees. And anything that was on the right except for the nucleophile. Anything that was on the right is now going down, and anything on the left is now pointing up. Okay, not the nucleophile, because that's going to be doing the attacking, so it can't point up. It points neither up nor down. So that's the reason why carbon 2, remember in the numbering, this is technically carbon 1 because it's the aldehyde. Carbon 1, carbon number 2, so just carbon number 2 is going down. It's going down. Carbon 3 is going up. Carbon 4 and carbon 5, well, carbon 4 would be going down. And carbon 5, it doesn't. The alcohol is the nucleophile. Okay, then we have what I call the scorpion's tail. That is not the scientific term for it, but it just kind of reminds me in the very end like a little scorpion. Alrighty. So what happens here is we can imagine this alcohol. What happened? Oh, I think my pen was dying. I thought I charged it long enough in the last class, but not. So this is going to be really fun. Yep. This alcohol here could, in theory, either attack from above the plane to smash that carbon. And if it did, the new alcohol, whenever, I really wish I could have another stylus, because this is not going to draw very well. I apologize. But we can imagine if it comes from above and it smacks that carbon, we're going to have something has to break or give. And what breaks or give is that double bond, right? And it's going to come up to make the alcohol. Well, if the nucleophile came and smacked from above, the alcohol is going to be pointing down. If this nucleophile came and smacked it from below the carbon, on the bottom side of the carbon, then the resulting alcohol will be pointing up. Okay, and so that gives you an even more complexity to the stereochemistry. So they give each of these special names. Almost all of the sugars that naturally occur in your body that your body uses, almost all of them are Ds. Okay, so that's why the default whenever I talk I'm going to be using, you just assume that they're D. If you start with a D sugar and the resulting alcohol is on the same side of the same face, if you think of the cyclohexane ring, it's not cyclohexane ring, but it's a cyclohexyl ring. If the alcohol and the scorpion's tail are on the same side, it's called a beta, the beta form. If they're on opposite sides, like for example, this one is on the bottom and the scorpion's tail is on the top, it's called alpha. The way that I remembered that is alpha and opposite both start with vowels. Like I said, there's all the memorization in this chapter. Whereas beta and same both start with consonants. And since my pen died, I had to use my fingers, and so my handwriting will be even worse than normal. So that's how I remembered. So this was technically called beta D-glucose. This one's alpha D-glucose. And what we'd find out, there are enzymes that specifically recognize, or could possibly recognize one form more preferentially over the other form.
Do we have both of those?
You do. Mm-hmm. And what we're going to find out is you can take these simple sugars, and when you start making disaccharides and trisaccharides, they have different chemical properties when you start hooking them up together. Okay, and we'll look at some examples in a moment. And then there's another term that I wanted to point out. See here it says a pyranose. Pyranoses literally are sugars that are cyclical that have 6 carbons. They're 6 carbon membered rings. So they're called a pyranose. I'd write that all out, but I don't have enough room to write with my finger. Okay, I can with a pen, but not with my finger. So if it's a 6 carbon ring, it's called a pyranose. Does anyone remember what it's called whenever it's a 5 carbon? Because I mentioned it like briefly in organic chemistry too. We have pyranoses and we have furanoses. Okay, and I'll show you examples of that in a moment. Okay, but of 6. So that's why you could also have like a glucofuranose, which would be a 5-membered ring. You'd have a bigger scorpion's tail. Okay. Then they give the carbon that determines whether it's an alpha or a beta. It's got a special name. It's called an anomeric carbon. And just remember, that's the carbon that got attacked. So the carbon that got attacked is called the anomeric, because that's the one that dictates whether it's an alpha sugar or a beta sugar. biochemists love alpha and beta, in case you couldn't tell. Alpha helices, beta sheets, alpha subunits, beta subunits. We talk about things being alpha with respect to each other means that they're next door. Beta means it's two atoms removed, so on and so forth. They like their Greek letters. Well, I mean, especially those, because most of the time when you're talking about the reactivity, you're talking about just either one or two atoms removed. But in like lysine, they say alpha, beta, gamma, delta, and so they'll say, oh look, it's delta, and it's called the epsilon amino group because it's the fifth one down. But we just don't. Yeah. I mean, this is lysine. All right. Well, that's just looking at the same thing. That's just to show you, to remind you of what axial versus equatorial is, and you can look at it on your own. I'm not going to go into greater detail here.
Is this, I keep seeing 13 in the corner. Is that?
That's from the old book.
Oh, okay. So it was chapter 13.
Mm-hmm. Yeah, no, it's chapter 7 in this book. Yeah, the old book, many, many years ago, back whenever this was just a single, believe it or not, this used to be a one semester course, and we had to go really fast. Really, really fast. It didn't go into as much detail, and I really didn't like it, especially for the metabolic pathways. It was really light. It's something more similar to what you'd see for like a nursing class, I would say. Okay, and so as I mentioned already, we have I thought that was a highlighter. We have furanoses, which, and they're named that way based off of, because it kind of looks like the compound, the organic compound furan, and purinoses because they kind of look like pyran. But that just, remember, like literally it means if it's a 5-membered ring, it's called the furanose. If it's 6-membered, it's called purinose. That's why the one that I'm used to seeing the most, because given my background, is DNA or RNA, which I really apologize for how crappy this is going to draw out. But, sorry, that is really bad, but hopefully you get the idea. That was a furanose. DNA, like the sugar, the ribose that's used to make the DNA or RNA backbone, is technically a furanose. So it'd be ribofuranose, because it was originally ribose, and it's in the furan position. You could make it pyranose, but that's not the one that's biologically relevant to make DNA or RNA's backbone. That's not to say it's not relevant for something else, but okay. I'm going to skip all that. Alrighty, because those are just saying the exact same thing. So sugars themselves, since they have so many alcohols, you can imagine, if you think back to organic chemistry, they can be further oxidized, because you can turn an alcohol into an aldehyde or ketone, and then you could also turn it all the way to carboxylic acid if you wanted to, okay? Or you could go backwards and go back to the alcohol. So remember, just in general, whenever you're increasing the number of carbon to oxygen bonds, you're oxidizing it. If you're decreasing the carbon to oxygen bonds, you're reducing it. Or another way to think about it is if you're increasing the number of carbon to hydrogens, then you're reducing it. But it's really easy to tell with sugars if they've been oxidized or reduced, because here in this instance, this one is an oxidized form of this, right? Because we've increased. And I realize, I always tell you to memorize this term, but I realize almost everybody from organic chemistry too will forget it. This type of functional group here, that's an ester, but does anyone remember what cyclical ester is called? I always liked it because it sounds like a musical group from the 1960s. They're called the lactones, which doesn't sound like an all-girls group from the 60s. These are the lactones. It's technically, this is a lactone formation. It's an ester, but since it's cyclical, it's called a lactone. All right. So if you go all the way back to Gen Chem, if you remember, something that gets oxidized is called a reducing reagent, which to me always seemed backwards. Always did. And even to this day, I always have to really think it through slowly. So because this sugar can be oxidized, it's a reducing reagent because it reduces whatever oxidized it, which, like I said, I apologize, to me is so backwards. But that's the reason why that any time that happens, if you have a free alcohol here, like this one, that could be oxidized, that's called a reducing sugar. Okay, that's really important. So that when we start stringing these together, there will be one end that's called the reducing end. And that's important, especially when we talk about like blood groups and blood typing and stuff like that. They'll talk about the reducing end of the antigen response and stuff like that, the reducing sugar. Okay, and that's because one of them is going to have that alcohol on the end. And it may even be, which I have a picture to show this, like it just astounds me. And I'd always show this in forensic science and it's lost on them. Like the beauty of it, or the fatality. I don't know if you think of it glass half full, glass half empty, life is precious, life is fleeting, whatever your life look. But it's amazing. The only differences between the blood groups literally can be just like what's on the end of that sugar. Okay, and it's literally life or death. But I just wanted to point this out, that this is called a reducing sugar because it can be oxidized. And this is called Toland's reagent. It's silver. It's really cool. I used to try to do this sometimes in organic chemistry or gen chem to show what happens. I didn't ever do this in biochemistry lab, but it's really cool because it forms a mirror. So if you put a sugar in a test tube that's got like the round bottom test tube, and you stick in Toland's reagent, it forms this mirror. It looks like a mirror ball, and because the silver gets plated on there, and so you can then turn it upside down and it reflects everything, and so it's just like a mirror ball, like you see out in like decorative gardens and things like that. I don't do it because it's so expensive. Silver is so outrageously expensive. It's just not very feasible now to demonstrate this. Okay, sugars can also be reduced. So the aldehyde or the ketone, here's an aldehyde, because this is glucose, can be reduced. And when it's reduced, they're called, it's called an alditol. But we use this all the time nowadays because a lot of these are used for sweeteners. Because, glucose is blood sugar, but, you've got to keep your blood sugar in check. Right? You don't want to have too high glucose or too low. And so sorbitol is one of the sweeteners that you can use. It's used many times in like sugar-free gums and things like that. It's just sorbitol. And all it is they've taken, glucose and they reduced it.
Is it something that a lot of people have allergies with? Or I know people with allergies. I don't know if it's that though. It's a sweetener.
I'll tell you right now, anybody can develop an allergy to anything.
Yeah.
There's just some that are just more common. But sorbitol, once you'll hear, it's more of a wives' tale, like a folklore, but it is true, but you have to do a lot. Sorbitol is also a laxative.
Oh, really?
And so, it is true, some people are more sensitive to it than others, but you'd have to chew lots and lots and lots of sugar-free gum before you have to worry about messing yourself, okay? But I used to try to relate this to organic chemistry, what would this be? But just to do time, I won't. If our body can't use nickel, obviously we don't do this in our body, we have enzymes that do this kind of thing. But, you can use that hydrogen with like nickel, rhodium, platinum, something like that, and you just turn it into an alditol. But you can do that with all the sugars, and in theory you can turn these. And so that's where we get some of these, mannitols and erythritols and some of those alditol sweeteners are just based off of that. That's why I always cringe when people say, "Oh, but it's not natural" or whatever. I'm like, well, technically, it is a natural sugar. I mean, it is. It's just that our body doesn't elevate or depress our glucose levels because the fact is it doesn't recognize it as being an energy source. Our tongue just recognizes it as being sweet. But once again, all things in moderation. Well, I shouldn't say all things, but this in moderation. And the very last thing that I wanted to point out and where I want to leave off on is the fact that you may have heard of glycosides or glycosidic bonds. All that means is now you can start to take things, and since it's an alcohol is a great nucleophiles, you can now actually start and replace that alcohol and have that alcohol go and attack other things. And whenever that happens, is you can start putting other functional groups on it. And we'll talk about in the next class period. some of the different functional groups that can be added on or removed and things like that. And in the form, that bond that happens is called a glycosidic bond.